Thanks a lot. Good morning, by the way. I'm a little bit jet lagged because I flew from California. And this is the exact route I actually took several days ago from San Francisco to Copenhagen and then to Brussels. And, when I think about like commercial flights, we usually think that, hey, you're going through some security and then getting on the plane, flying, eventually like getting some drinks, snacks, and landing and leaving the airport, right? But the reality of commercial flights is actually more complicated than that. Like, it's so complicated that as a frequent flyer, I actually am appreciating that, even the, cancellations and delays, like there's so much going on, and there are zillions of things that need to go right in order for them to fly me from San Francisco to Brussels. And I actually, as a customer, like I don't really have visibility to what is going on. So my experience was more like, hey, I arrived at San Francisco airport. The airport was functional. The security was still working. I went through security. They validated my identity. I spent some time waiting for my plane. Everything like traffic control was working. Like no planes were crashing over us or whatever. The gates were working, the announcement system was working. They started to announce that they're boarding, and I ended up like boarding the last. We closed the doors, and I got on the plane. So our pilots probably went through all these like different checklists, and I assumed that they were all green. And they pushed our plane. Traffic control allowed us to leave just slightly earlier, so everything went well. And finally, we were just, flying. We use all these, like, different facilities. I mean, just imagine, like, all this stuff that you are engaging when you're flying, and all the facilities that you are actually using, but none of these facilities are actually reserved specifically for our flight. But they are really essential for our flight to happen. So I had a comfortable seat, whatever, good food. I actually flew, and engines kept working. Time passed quickly. We actually ended up landing in Copenhagen, and I went through the border and made it to my connecting flight and landed in Brussels. So anything could have been wrong, right? Like including the details, I don't know. And imagine all the like ground staff, the flight staff, the machinery, the electronics, everything involved, and as well as the border enforcement. So it requires a really complex system of cooperation to fly somebody from San Francisco to Brussels. And it's not always, the things are not always good. Things may go wrong. As I said, that there are cancellations, delays, whatever. Different components of the system may fail differently in isolation. And we sometimes don't even realize the existence of these like small subcomponents until they fail, because we don't really have like visibility. As a person who is flying, I don't have a lot of visibility into commercial flights. You don't really appreciate a lot of good things because you just assume you just don't have a lot of visibility. For example, if you return from the border when you were trying to get into the Schengen area, you wouldn't appreciate all of a sudden like, hey, all this stuff until now like worked out fine. You actually were promised to be flying to Brussels from San Francisco, but you eventually had to like return back earlier. Anyways, like any computer system is actually like flying. Our users engage with a really tiny part of the stack, and that's their experience. So your billing infrastructure, for example, may work so well for the most of the time. But if a user transaction doesn't go through, it doesn't mean like that's the end of the game for that particular user. So let's talk about a little bit about our everyday computer systems. So I don't think that like we have a lot of visibility into our stack, and I don't really think that like everybody thinks that they scale in terms of both development, maintenance, and generally the production experience. If anybody thinks that they do, I'm really impressed. Like I worked at so many small and large companies, and never thought that we did. At my current company, I kind of feel like we do, but there are so many small gaps here and there. Today's talk is actually about like how we are trying to fill those gaps. So, by the way, I'm Yana. I work at Google, and I had opportunity to work on a bunch of projects, including contributing to some of our infrastructure projects. And I have several stories about my time at this company, and this is one of them. So, the early days of a company or a project is really nice because things are simple. You usually have a simple server and a few other components. Like you maybe have a Postgres cluster for your data. But everything is just kind of like fitting into your brain at this point. Your architecture is just like a few notes here and there. If somebody joins to the team, you're just taking the person to the whiteboard, explaining them what is going on in a couple of minutes. If there's something going wrong, you can take a look at the logs, and it's easy to debug things from the logs. And then the next step, you're growing, you have more engineers. The company culture is also changing because your monolith is not really, helping you organizationally to scale. Some teams want to push stuff to production more often. Some teams just want to, keep things more stable. So there are different demands between different teams. And, this is the point that you want to do something else and, breaking down your big monolith. So the growth is great, but you started to see the first symptoms of actually diversifying and fragmenting your tech stack. You start to include more stuff. You have more storage, more DBs, you have different queues or whatever. Each team is kind of coming up with their own ideas, and everybody is sort of siloed and not really talking to each other, and you have this huge mess because all the monolith organization is gone. And this reality is coming with a lot of new challenges because just this one single problem just became many. And you can't really depend on the earlier ways of doing things, especially in terms of debugging. You can't really, self-document all this stuff end to end because, it touches to a lot of teams and there's no coordination between these teams. And, reading the logs is just so hard because some stuff is here and there and some stuff is there, everything is failing in isolation or maybe just working well, whatever. You just don't understand the overall state of what is going on. And your engineers just really don't know what to do when things fail. Who's the person that we should contact? Everybody's kind of escalating stuff to each other because it's hard to pinpoint what is the root cause of the problem. And sometimes it gets larger, for some large companies, it becomes really intolerable. The companies like mine, it's actually such a big pain. And, a lot of people have been asking me, who really wants to work for such a large company? This was my biggest concern before coming to Google. I worked for another large company, and I just didn't want to, take the job because it would be a nice opportunity, but I will be feeling so unproductive because it will take me a lot of time to learn the stack in our systems. So in some cases, people think that key people like Jeff Dean might be the answer to all of these problems because, these people have been around for a long time. They have been there when initially all these conversations were happening about, critical parts of the infrastructure. They sort of have a better understanding of things end to end, but is this our strategy? Are we, keep escalating things to Jeff Dean? Nobody does that. And, Jeff Dean actually went to AI, but maybe this is partially why he went to AI because lots of people are still coming to him and he's trying to just basically replace himself with AI. I don't know. So anyways, to be more realistic, especially, very fragmented in large systems, everything becomes such a big mess. We have all these different services, different storage systems, different DBs who actually has invisibility. At some point, this is the typical meme we had at Google. We just need to delete all of this stuff. We have this huge complexity. The code is owned by different teams. Nobody knows how it works end to end. People who have been around for a long time actually have been burned out because they became the canonical source of truths, and they can't really take vacation because if they just take 2 weeks off, everything just goes south. And the documentation is not an answer to any of this because documentation doesn't really can catch up with the change. So docs always lie, they're always coming late, and you really don't want to depend on docs. So when I joined this company, on my first hour, like literally it was my first hour, they were like, hey, there is this thing called Code Search. This is an internal tool. It's called Code Search. It's basically a search engine for our internal monorepo. It's really amazing. It's just really, the ranking and everything is so easily. You can just really pinpoint to stuff. But the only problem, the restriction is, you need to have an entry point. You need to, know the symbol name, whatever, like the file name, or some sort of like entry point, project name, maybe username. You can actually see the history as well. So it's nice if you have an entry point. I use this every day, and everybody at Google uses this every day, especially if they're engaging with the monorepo. But it's partially why we can understand better about our systems. The second thing is we have this unified build tool, which is called Blaze, which inspired Bazel, the open source version. And since everybody's using the same build tool, it kind of makes things easier because you can actually like take a, click on a build target. You can see who is dependent on this build target and everything. But this is really good for static dependencies. It doesn't tell you anything about your dynamic dependencies, like service dependencies. So this is really cool, but it's not the actual solution. And none of these tools are really good in capturing like what is important in terms of pointing out to like the most critical execution paths. This is a typical system that returns some user profile images and a bit of metadata. And there are many services here. There are many services, we're going through some services and like as well as some storage in order to, return a response to the user. But the blue line is here what we call a critical path, because the user request comes in to the load balancer and hops through like a certain path in order to serve this request, and all the way down to the low-level disks. And at some point, we actually have a response. At my company, we actually put some emphasis making these critical execution paths more visible. So engineers can actually see, investigate, and debug. If engineers can really see this type of execution paths, they can also see what exact components were required to serve that request. They can also run some like analytics on like what type of like execution paths are important or what type of like service dependencies around. This requires some sort of like dynamicness. It's actually generated by data coming from the dynamic instrumentation in production. And it's a bird's eye view, for our systems. You can really understand the service dependencies and what paths and what dependencies and what relationships are more important. So just like my flights, our users don't often know much about under the hood. They don't know what is going on in our systems. They really expect this big black box to respond to them. They don't really care about the health or the availability of this underlying stuff either. They just expect a response. For example, if the user service here, one of the replicas just dies, just crashes, and the scheduler just spawns a new one in the lifetime of a request, and if the user cannot really tell because the latency was not that high, the user wouldn't care. So being able to think about your systems from the perspective of critical paths are really important, because the goal here is not the availability of these different individual components. The goal here is the availability of the user execution path. So some of the goals are the goals of critical path analysis. As I said, the availability of the underlying processes doesn't really matter at all. It's more about having the user experience up and running, having that critical path up and running. And it's just kind of like flying, right? I fly, but I don't really understand what else is going on. I know what I engage with. I don't care if the airport is entirely functional or not. I just want to use one gate. Maybe I will just, sit and eat. I just really engage with a small section. And from my perspective, that's what matters. So being able to, think about our systems and evaluate our systems, from the user perspective is a very different approach, but it's really useful. So some of our engineering practices are really around discovering critical paths automatically, and I briefly mentioned that we do this in production. And once we discover these critical paths, we also, use them as debugging tools, as debugging data. We want to make them, more reliable, as fast as enough. And if there's an incident in production, the data provides us some debuggability. We can just go in and actually see what has happened. If it's the middle of the night, if you're on call, you just really want to be able to see everything end to end without knowing too much about the entire system, even if you haven't, read the source code before. So that's cool, how we get there. There are different ways to do this, actually. We talk about like two main emerging tools in the industry nowadays. I don't know if you are interested, like if you are familiar with distributed tracing or event collection, but login can also be used. The tricky part of login is, it needs to have more context about the execution path. You need to like carry a request ID around, and you need to, structure maybe the log messages in a way so you can generate these execution paths by looking at parsing the data. So this is a very common way of understanding a problem. Just keep asking why, like being able to ask why. It's kind of like this golden rule of exploring, cause-effect relationships. So the granular, event collection or distributed tracing has this promise. It's kind of like, hey, we want to give you this ability to be able to go deeper in the stack and try to, help you what actually happened. This is why people sometimes say observability is about having answers for questions that you haven't had yet. Because, the question appears when there's an incident or there's some unlikely event. And you should have planned to, collect enough data. So if the incident is there, you should be able to take a look at your debugging data and should have answers to your questions. So I will show you some illustrations of some traces. I don't know if you are familiar with tools like Zipkin or like your network tab on, developer tools on browsers. Typically, traces look like this. There are a bunch of things going on. Each row here is representing a different component. Some different action is happening. It captures, this is what happened here, and how much it took, and where it actually initiated at. And here, what we see is this is a trace for an API server I have. So for /timeline, you can see all these different server components that I actually had to go and make RPCs to in order to respond to the user. So you can take a look at these, routes to learn more about the lifetime of a request. Like if somebody, for example, new joins to my team, and if they're going to work on the API server, they can take a look at the trace to understand, oh yeah, this is all this stuff. They don't have to read the code. They can start with looking at the trace and learn what is going on. So also, welcome to 2019. This is the basic stack we have. It's ever-growing number of layers. And maybe you have more understanding of your user space, but everything underneath, I don't know, what I called cloud stack, which is Kubernetes, whatever, it's just a big black box, and we absolutely have no understanding. Just imagine if your infra was providing some granule events or traces from that layer in the lifetime of your requests. If there's something relevant, it would be so much easier for you to understand. Imagine some of the, for example, Kubernetes scheduling decisions are leaked into the the networking layer because load balancer need to understand the scheduling decisions. If we can actually capture some traces from that layer, wouldn't it be nice if there's an unlikely event, unlikely scheduling decision, you will be able to just go and take a look at your user trace and pinpoint, hey, it was the scheduler or the load balancer. Because of this reason, this happened. So there's no way that we can learn this entire stack in our lifetime, but I think that this type of debugging tools allow us to understand more of each layer. So traces are a cross-stack debugging tool. You can basically use them to blame whose fault it is. Returning back to that API server thing, just imagine that the engineer just comes in and takes a look at all the we waited this much time for the scheduling decision to happen. So, that person can escalate the issue to the scheduling team because, hey, like there's this additional latency, but it's actually not my fault. So it kind of gives you this Git blame for production issues type of functionality, which is really nice. And it's really nice when your cloud providers are participating into your trace because what you can see is, hey, there's all this additional, latency coming from the cloud provider's load balancer. Maybe I can escalate this to their SRE, and this is the evidence. Because each time you escalate stuff to cloud providers, they're a little bit like, hey, are you sure that it's us? So, hey, here's the data, and it's the proof. The other thing is you can actually, it's really nice that you can build some tools to map this type of data to the source code. Here, for example, each bar, each span is representing an RPC call. So it would be nice to just, take it to the RPC, maybe, the handler or to the client source code. So you can take a look and just basically, review what has happened. Especially, it could be a, misconfiguration or a malformed payload or some sort of a stupid, timeout configuration that there was some additional retries or latency. So it's pretty cool to be able to do that if you build some additional tooling around this type of data. And the other thing is, who to call. There's an issue with this specific component. I am not the person who can understand. I read the code. I took a look at all the additional data, and I don't really know what is going on here. Who's responsible for this? If you have a catalog of different teams, if you can map one of these blocks to a team, to an SRE team, or a regular team, you can actually give them a call and try to understand what is going on in production. And the other thing is, give me all the other stuff you know about this block. In the lifetime of this block, what else has happened? Because we don't capture a lot, everything in forms of traces or something else. Would be nice to just, see what else is going on. A very typical example for this is, just the logs, because we already have logs everywhere. So just give me the logs. What happened? I just want to, understand more of granularly what happened. So nothing comes free, unfortunately, and I will explain some of the challenges. And I think we shouldn't undermine the level of investment required to roll some of these technologies in your organizations, especially if you already have an established organization. It's a little bit harder to, put these in. And this is where people usually got stuck. Especially if they haven't thought about these capabilities and some of these challenges early in the early days. So if you need critical path analysis, it actually is a cross-team problem. So the entire organization needs to agree on a bunch of things. They need to agree on, you need to do some instrumentation in order to be able to generate that data. You need to be able to collect those hey, this is the start, this is the end, whatever. But you need to just be able to reconstruct the trees. So you need to really propagate some request IDs around. And there is not a lot of agreement on this, there's no golden standards or whatever, even though for distributed tracing, at least there's a W3C proposal coming up. But apart from that, there is actually no real standard. And just imagine that even if you internally understand, even if you internally agree on one particular identifier format, you are hopping through these different load balancers or whatever, and they don't really understand that format. So we really need an industry format for that, and for distributed tracing, we're actually working on on a standard. So that's really good news. The other thing is engineers really don't know where to start. Hey, we can capture a lot as a part of traces or event collection. We usually say that hey, start with your network stack, specifically HTTP and RPC. And this is actually where things are getting really easy, because if you have a framework, or if you can start things with the load balancer maybe, you just get some automaticness. You can, for every RPC or every request, you can just automatically generate one of these bars. And you can simply start by using an instrumentation library that works well with your existing frameworks and gather some data from there. The other thing is infrastructure is still a black box, and none of the vendor services are really designed with these type of capabilities. Nobody actually considers about these capabilities in the first place. We still expect people to learn a lot about the underlying stack by reading the code, docs, talking, and we don't expose this type of debugging information. And it's a huge challenge, especially if you are running stuff in managed environments in your cloud provider. For example, serverless function running environments where you basically do not have a lot of control, and if the environment itself was automatically providing this type of debugging information and you can participate into that, that would be so nice. The other thing is, instrumentation is really expensive. High traffic systems really, end up downsampling, and it's a huge topic. What kind of downsampling strategy makes sense? And we sometimes miss, collecting data for interesting cases, and we want to just improve this over time. And we only have a few brief, ideas what to do. And the other challenge is the dynamic capabilities of instrumentation has been underestimated for a long time in the industry. And this is really important because we ideally want to be able to tweak things. We want to be able to collect more maybe if there's an issue. But doing it in a safe way is not really easy. So this is still a big challenge. You need to have your own strategy. And to kind of wrap up, we are still kind of in the dark ages when it comes to understanding and maintaining our systems. When I talk about these concepts, I just feel like I'm this snake oil, salesman just traveling and talking about these concepts. But I have to say that we have some sort of some of these abilities actually at my company at least, and it really helps us. It makes your engineers slightly more happier. Because you can give them an overview of what is going on, but at the same time, this is not the end game. It's just an overview, and it really just changes the way you interact with other teams and everything. But it's just a entry point tool, not the entire solution. So I just want to say that this is a tool that really closes knowledge gaps in our organizations, and we don't talk about it. I think I came here to talk about it. And I would love to, answer your questions if you have any. And thanks much for having me here.
Please sit down during questions.
Be quiet when entering. Be quiet, and remain seated for now.
Hi, Jana. You said that you're not aware of a distributed tracing standard. That's why I understood open tracing to be that standard. Can you explain maybe why that doesn't fit in with this, or?
The question is open tracing is a standard, or I mentioned the lack of standards and how open tracing is not aligning with that?
Sorry to interrupt. Again, about respect of the speakers and their time and their commitment, can you please be quiet? Thank you.
The question was the question, I mentioned that there are lack of standards, that there are not a lot of standards around, and you mentioned open tracing. So the question is open tracing not a standard in Okay, so open tracing actually provides some hooks to instrument things, but it's not opinionated about the propagation standards, or it's not opinionated about the data you export. So and you need to so each provider has a different, is enforcing a different data export format and a header format. And if you're using open tracing, you need to link the entire system with the one specific, implementation of open tracing, so you can have like end-to-end stuff. This is not like practical. For example, if you have Nginx as a binary, Nginx just doesn't know much about whatever tracing provider you want to use. So we want to make this less of a build time constraint, but more of like a wire format, so everybody can understand the same header and produce similar type of data. So nobody actually like has to rebuild stuff in order to have traces. I hope that answers your question.
Hi, Anna. My question was, can you go into a bit of details of what you meant by dynamic constraints? Yeah, dynamic capabilities. Would you have an example to elaborate this?
So one of the typical questions is like, how much data should I collect? Or, how granular should it be? Or sometimes we collect distributed traces, but it's not enough. Like we just need to go and enable some other stuff momentarily. For example, it's a very common thing at Google that, hey, we just don't know, like there's some additional latency here. It turns out sometimes ended up being the GC latency. In order to capture that, like you actually need to have some runtime events coming from there. And it's not like really, in the scope of distributed tracing. So you just need to go and like tweak a few other things and, enable some more instrumentation and need to be able to correlate in a way with that distributed trace so you can still capture that, like, hey, this is what has happened in the lifetime of this. So that's kind of like what I mentioned. And again, it's a huge topic. It's more about enabling more signals, maybe adding more granularity, maybe adding more debugging information, maybe adding more like granular other stuff. It's all in the scope of dynamic capabilities, and we just don't really think too much about it when we're developing things. So yeah, it's something that is not very ideal nowadays.
Hi, and thanks for the talk. You were mentioning freeing ourselves from like build time constraints and stuff like Nginx and things like that. Do you think that we can ever automate this sort of dynamic instrumentation, given that it seems to require at least some degree of domain knowledge that at some level has to be input by humans?
So the question is, if we have some sort of standards, is it possible to automate all the distributed tracing by putting this in our load balancers, Nginx, or in similar stuff? So there's, you can actually start a trace, but you still need to propagate it all across in your stack. That still becomes a problem. We can just generate the RPC level, the ingress, maybe request span, but you still need to, just put the right header to the outgoing requests, and all the other stuff need to align with that and sort of like participate into that to have actual any meaningful traces. So it's not really easy to do this, especially in language runtimes where for example, for Go, it's really hard because you need to be in the runtime propagating the right identifiers. In some language runtimes, it's like so much easier, especially if there's one single thread, or you can just really put the context in the thread. So it depends on also the language, the language and some sort of like capabilities and limitations around that. But it's the actual answer is unfortunately no. There's no like super automatic magic way.
Hello, thanks for the talk. Yeah, here.
Oh,
yeah, sorry. So you've mentioned that infra is still a black box. Do you think that things like open compute is the way to go to solve that problem? Or anything like that, like open source
Did I
Talua?
mention, can you repeat that again?
Yeah, so you mentioned that infra is still a black box. And do you think like things like open compute is the way to go to solve that problem?
I'm not really familiar with open compute, but lots of infrastructure builders really want to like expose this type of data once there is a real standard, like an export for like standard, for example. They want to provide like a hook or whatever. They will just write it like in a whatever particular format, and they want to be able to expose, and they want to really like work with the user trace. It's just like the more of like this like lack of wire standard at this point that nobody's interested. But I want to take a look at open compute, but because I don't have much context about it. Maybe we can chat after this.
Okay. Thank you.
Thanks.
Hi. Is it any projects like going on? You mentioned the guy going to AI. Do you try to implement some AI machine learning technology to get like, okay, we have some problems and it's analyzed and then some suggestion where it can be?
So the question is there any AI work related to consume this type of data?
Yeah.
There's actually a lot, especially in the scope of anomaly detection. They want to be able to automatically say that like this pattern, this usage pattern, this pattern is not really normal. There's some additional latency or like different components or additional number of retries and everything. So they just want to use some sort of like I don't understand what they do at this point. I haven't spent a lot of time reading, but they want to do some better recognition of unusual patterns by looking at the data.
Thank you.
Oh, thanks.